Let's look at the solutions of number system bytes for this day. T is equal to 1, 2, 3, 4, 5, whatever number, n raised to the power n up to 50 raised to the power 50. What is the remainder when P is divided by 8? Okay, now 8 is 2 cube, which would mean any even number raised to power 3 or higher will be divisible by 8. So can I say apart from this number, which is 4, every subsequent even number raised to itself would be divisible by 8? So we don't really care for these numbers anyway. These are not really bothering us because they are directly divisible by 8, even 10 here, and all the interim even numbers. This one somehow survives. Now the rest of the odd numbers, I have 1 raised to the power 1 plus 3 raised to the power 3 plus 5 raised to the power 5 plus 7 raised to the power 7. I've written down only the first 4 numbers because see, whatever remainder you are getting here, can you see for 9 raised to the power 9, for 9 raised to the power 9, storyline will be same because it is 8n plus 1. It is 8n plus 1 raised to the power 9. And let's say for 11 raised to the power 11, it is as good as 8n plus 3 raised to the power 11. Similarly, for 13 raised to the power 13, it will be 8n plus 5 raised to the power 13. And finally, for 15 raised to the power 15, it would be 8n plus 7 raised to the power 15. This much is going to be identical. So can I say what I actually have? What I actually have is 8n plus 1, 8n plus 3, 8n plus 5. Everything I can happily get rid of. I can straight away say or oops, second question. Okay, I can say this is 1 raised to the power 9 plus 3 raised to the power 11 plus 5 raised to the power 13 plus 7 raised to the power how much? 7 raised to the power 15. And this storyline will keep on happening for every 4 odd numbers, every set of 4 odd numbers. How many odd numbers do we have? We have 25 odd numbers. So we will have 6 such groups. We will have 6 such groups. And finally, I will have 1 raised to the power 49 extra. Another fun thing, the Euler number for 8 is equal to 4 itself. Euler number for 8 is equal to 4 itself, which means I don't need to look at 5 raised to the power 5. I can happily replace it with 5 raised to the power 1 and 7 raised to the power 3. And if I can replace it here, can you see I can also replace this with 1, this with 3, this with 1, this with 3. Effectively, each such grouping will happen 6 times. There were 25 odd numbers. You have made groups of 4, 4, 4, 4. So there will be 6 such groupings. Now for this one grouping, let's see what the remainder is. I get 1 plus 27 plus 5 plus 343. This is what we are getting. See, 27 plus 5 is 32. So out. And 343 plus 1 is 344, which is nothing but 320 plus 24. So this is also divisible by 8. This entire group is divisible by 8. This entire group is divisible by 8. Every group that gets created will be divisible by 8. So we can leave it alone. The only thing that is left is this number and this number, 2 square, because every other even number is divisible by 8. So finally, the remainder that I have is 1 plus 4 upon division by 8. Answer to the question will be 5. Next, how many multiples of 18 are there that are less than 3500 and also 2 more than the square of a natural number? Now, the idea that you have to get here is cyclicity. If you find one such number, hopefully all of you can see The smallest such number, hopefully you can identify, is 4. A multiple of 18, that is 2 more than square of a natural number. The smallest such number is 4. Now 4, the next such number is going to come after a gap of 18. Let's look at 22. Let's look at 22. Is 22 square, which is 484. Sorry, 484. If I add 2 to it, it turns to 486. Is this a multiple of 18? Very much so. Divisible by 9 and divisible by 2. So 22 works. Basically, it is because of family of numbers. If 4 works, then 18n plus 4 works. We are basically saying all numbers of the variant 18n plus 4 will give me a number, will give me a perfect square, to which if I add 2, I will get a number divisible by 18. All of these would work. In fact, this initial 4 is also a hint. Can you see if you've got it for 18n plus 4? It should also work. It should also work for 18n minus 4. Because even when you square this up, you will get 18n whole square plus 2 into 18n into minus 4 plus 16. You had an extra plus 16 here. You have an extra plus 16 here. If I add 2 to it, yes, this will become a multiple of 18. So it is not just 18n plus 4. The other good variant is 18n plus 14. Okay, so all numbers of the variant 18n plus 4 and of the variant 18n plus 14 are wonderful. But there is an upper limit also. We want numbers that are less than 3500. 3500, square root of this number, square root of 3500 would be around 60. Would be around 60. So up until 60, we are not stopping. So 4, 22, 40, and 58. 58 square, is it less than 3500? Most definitely, because 39 square is 3481. 59 square is 3481. So 58 square is definitely lower than this. Here, if I start, the list of numbers would be 14 plus 18 is 32 plus 18 is 50. I can't go any further because I will cross the threshold of 60. So there are 3 numbers here, 4 numbers here. Altogether, there are 7 such numbers. There are 7 such numbers whose square plus 2 is a multiple of 18. Okay. The next question. All possible 4-digit numbers are formed by using the digits 3, 5, 6, 8 without repetition. Out of all such numbers formed, how many numbers are divisible by 4 but divisible by neither 8 nor 11? Okay. So we want numbers that are divisible by 4 but not by 8. So basically, if the number is divisible by 4, can I say the unit digit has to be even? Unit digit. First, let me ensure it is divisible by 4. So I've got 6 at the end. The 10th digit can either be 3 or 5. This is done. Okay. Now, if it is 836, can I say it is definitely not divisible by 8? If the last 3 digits are 836, the number is definitely not divisible by 8. 800 plus 36, not divisible by 8. So life is chill. If it is 856, no, it would not work. 800 plus 56, it would become divisible by 8. So 8 will not come here. 3 will come here. 356. 8000 plus 320 plus 36. Okay. And here I would have 5836. So I found 2 numbers. I have to check additionally, are they divisible by 11? I get 14 minus 8. So no, this is not divisible by 11. I get 9 minus 13. So no, this is not divisible by 11. So these 2 numbers fulfill the criteria. Or I have listed down all the cases where the unit digit is 8. Now let us go to those cases where the unit digit, where the unit digit is 6. Let us go to cases where the unit digit is 8. Because unit digit is 8, I want the number to be divisible by 4. I have to get 6 at the second last spot. 6 at second last spot. Now, if I go 568 here, will it be acceptable? 568, would it be acceptable? 560 plus 8, no, this is not possible. I cannot have 568. Can I have 368? 320 plus 48. No, this is not acceptable, which would mean no other case is possible. I cannot have 6, 8 in the last spot, because if I place 3 prior to it or 5 prior to it, this number will become divisible by 8. So I cannot have any more cases. I cannot have any cases with unit digit as 8, and no other cases are possible. Therefore, the answer to the question is 2. Next question. When 907 is divided by two two-digit numbers, n and n plus 2, the remainder obtained in both the cases is x. Then the value of x for the maximum possible value of n is. Okay. See, essentially what we are saying is n into n plus 2 plus k is equal to 907. And we want to have as large a possible, we want to have as large a value of n as possible. We want to maximize the value of n. The trigger or the idea, very, very, very intuitive way to solve this is, can you see the greatest perfect square under the number given to you? The greatest perfect square under the number given to you is 900. Now, this is a square of 30. This is 30 square. So the number that you want here is 29 into 31. 29 into 31, because one number under perfect square. Let's say you have a perfect square n square. Can you see n square minus 1? Or I should not work with n. Let's say p square. P square minus 1 will be equal to p minus 1 and p plus 1. Numbers that differ by 2. Which is what we wanted here, numbers that differ by 2. So once we've identified 30 square, one number under that, we get 899. So it is 29 into 31. This is the largest possible value of n. In this case, 29 into 39 is 899. So what will be the remainder? What would be x? The question has defined this as x. It has to be 8 for me to get to 907. So the value of x for the maximum possible value of n is, the maximum possible value of n is 29, but the question is asking value of x, so the answer will be 8. Last question. If p be the product of all the natural numbers between 45 and 293 that have an odd number of factors, what is the highest power of 12 in p? Okay, numbers that have an odd number of factors are perfect squares themselves. So we are starting off with 45. So we are starting off with 7 square, then 8 square, then 9 square, and under 293, the largest perfect square would be 17 square, 10 square, 11 square, 12 square, 13 square, 14 square, 15 square, 16 square, 17 square. This is P. Now I want the highest power of 12 in P. 12 is composed of 2 square and 3's. So I have to count how many 2's will I get at every place. Here I will get 6 2's. Here I will get 2 2's. Here I will get 4 2's. Here I will get 2 2's. And here I will get 8 2's. So how many 2's? 10 plus 10 plus 2. So I have 22 2's available. But I don't want 2's, I want 2 squares. Can I say I have 11 2 squares available to me? 2 squares available to me. Now let me engage in the same count for 3's. Here I will get 4 3's under 9. In 12 I will get 2 3's. In 15 I will get 2 3's. So I have 8 3's available to me. Given that I need at least 1 3 and at least 1 2 square in order to make a 12, the highest power of 12 in P would be 8. Hopefully you see all the questions in this, all the questions for this day, all of them are not solvable by standard formula. All of them require understanding and intuition and practice, and there is a purpose behind giving you all these questions on a single day. Hopefully you saw the utility in that and you learned something. That will be all. Okay, bye.